Okay, well, thank you very much for the invitation. It's a great pleasure to give a talk. Okay, so everything I will talk about today is joined with Jean-Benoît Bost. Okay, so I want to talk a little bit about affine varieties in the context of arithmetic geometry. So I will sort of I will try to put a twist on these kind of objects, and I will define actually what I think is a good avatar of affine varieties in some kind of Arakelovian context. But actually, maybe so I gave a few lectures here a couple of weeks ago. So I want to stress that what I'm going to talk about is fairly independent from what I'm going to say. But for those of you who had to sit through the whole machinery, one of the goals here is to give fairly self-contained theorems that use some kind of cohomological machinery. Okay, so the first thing I want to talk about is two very classical theorems. So some classical theorems on arithmetic curves. So, okay, so the first thing I want to talk about is things around Fekete's famous theorems on algebraic integers in some compact. Okay, so I take K inside of C, a compact subset. Okay, let's say that K is invariant under complex conjugation. So this is a fairly innocuous assumption for what I'm going to say, so let's assume this. And then we may define, this is just potential theory, the capacity, which is also called the transfinite diameter. Of K. So there are many ways to define it, but let me just give one. So you said the following thing. So you define dn of k. I should say the capacity is a measure of the size of k in the complex setting, in the sense of complex potential theory. So capacity is exactly like you learned, I don't know, in high school or undergrad physics about electrostatics. So dn of k is the following thing. You look at the following thing. You look at a bunch of points, Z1, Zn in K, and you look at the max of the product of the distances of Zi minus Zj, like this. So maybe I needs to be different from J, and then you average it out. So there are n times n minus 1 pairs. So you look at this. Okay, so you look at the max, the way you can put points in K that are the most spread out, okay? And an easy fact is that dn is decreasing sequence, so dn of k is bigger than dn plus 1 of k, while of course being positive. And so let gamma of k, so this is the capacity, be the limit as n goes to infinity of this dn of k. Okay, so you can think of a lot of things. There's a lot to be done in terms of what the capacity is. Of course, you can look at how the points that realize this maximum sort of spread out inside K. You can do lots of things. But anyway, let's do this. So this is a non-negative number. And it measures like the big, of course, if K is bigger, then you can make this bigger. Okay? And so the theorem that is a very famous theorem of Fekete in the 1920s, I think it's 1923, is the following. So let k be as above with gamma of k strictly smaller than 1. Then, okay, so we can do the following thing. I look at the set of alpha in z bar. So z bar is the algebraic integers in C, such that all conjugates of alpha lie in K. So this is finite. This is a finite set. Of course, the easiest example maybe you can think of, you take for K to be a disk of radius strictly smaller than 1, then by a very simple norm argument, you only have 0 as an integer, all of whose conjugates lie inside the unit disk, because the norm has to be 0. Okay, so this is a very classical theorem. It's actually sharp in the sense that if gamma of k is strictly bigger than 1, you actually have infinitely many such integers. But that time, this is a theorem of Fekete and Zege, which is also very famous. But I'm not going to talk about this kind of converse because I don't think it holds in a, it's a more specific theorem, I'd say. Okay, so maybe I should say, so of course here we are arithmetic geometers, so you want to think of these kind of things. So the kind of thing you want to generalize about k lying in C, so we may replace, and I won't state the precise theorem, but we may replace A1. Okay, so there is, of course, underlying this, there is A1 over Z, right? This is K in C, C is A1 over C, right? And we are looking at algebraic integers, so there is this curve here. So we may replace this with any arithmetic surface. X, and we take K inside X of C. And when I say we may replace, I mean there is a statement exactly like Fekete's theorem in that context, where we can define the capacity of K, and we can say exactly when Fekete's theorem holds. And this is due to Rumeli in 89, I think. There is a nice book by Rumeli on capacity theory on curves, which generalizes this, and I don't think there is too much on the higher dimensional case. Okay, so that's one thing. That's not right. That's the one. Okay, so that's one theorem that I want to talk about. And the other theorem, which is a little less famous, I'm going to state it in a way that sort of combines a lot of different works. So there are statements around this due to Fekete himself. Then there is also things due to Gelfond. There is some mathematician named Le Baron, I think. So this is all between, let's say, the 50s and the early 80s. I wanted to do something very, very simple. So let K be as above. So exactly the same situation. So gamma of K is strictly smaller than 1. The capacity is strictly smaller than 1. So Fekete's theorem applies. And so, OK, so let alpha 1 up to alpha n be the finitely many algebraic integers in K, well, let's say predicted by Fekete's theorem. Okay, so we have these finitely many algebraic integers inside, all of whose conjugates lie in K. And the kind of question I want to look at is a very basic question. I take a holomorphic function on an entire function on the whole complex line. And I want to see whether I can approximate it by polynomials, by integral polynomials. So let f be, let's say, a holomorphic function on, let's say, a neighborhood of K of my compact set. And then the followings are equivalent. So I have two conditions. So F can be uniformly approximated by elements of Z of X, by polynomials with integral coefficients. Okay, where? So on a neighborhood of K. And so how do I check that something is approximable by polynomial? So I have a bunch of conditions. So first, I need, okay, so what do I need? I need, so for all x in a neighborhood of K, I need first, of course, these polynomials are conjugation invariant, so I need F to be polynomial invariant, so I need this F of X bar is F bar of X. Okay, so I need this. This is very mild. And the second thing is that, of course, as soon as I have an integral point on my compact, then I need F to take integral values there. And much more is true, I need the power series expansion of F at this point to be integral. This is very easy to see. So for all I, the power series expansion of F at alpha I is integral, has integral coefficients. Okay, so these two things are necessary. This is not a very good way to phrase it, so I'll rephrase the second condition in just after stating the theorem. But okay, so this is a consequence of the theorem. So for instance, if you're in a situation where you have no algebraic integer lying totally in the compact, then essentially any conjugation invariant holomorphic function can be approximated by a polynomial. The only obstruction comes from the integral points. Okay, so this is a fairly classical theorem. So maybe let me say let me do some remarks. So there are some variants due to the same people as above. So we have less variants, as far as I know, in the literature than Fekete theorem itself. So you may replace. Okay, so you have Z of X. So you can replace Z by OK with K, I think, quadratic imaginary. I don't even think. I think there are some conditions like this. So when I say this, I always mean there is a statement making this. You may replace C, so K is a subset of C, with C to the n, I think with K a polydisk, around 0. Okay, so there are some results with C to the n. I don't think there are any results for general arithmetic surfaces. Anyway, also there is a huge literature relating capacity theory in a compact and approximation of functions on K by polynomials, where you look only maybe at continuous functions on K or slightly different hypotheses. So there is a lot of literature there. So anyway, so okay, so my goal here is give general versions of these theorems. For arbitrary, okay, so the kind of objects that I want to talk about is so-called A-schemes. So I will talk about them in length, but an A-scheme is actually a very simple object. This is just an object curly X, which is a pair X and K. This is fine type separated over Z, an arbitrary scheme over Z, which is just fine type separated, and this is a compact in X of C, compact at infinity, which is a conjugation invariant. And what I want to tell you is that for such A schemes, I can define what it means for a pair like this to be affine, in some sense, either affine or I will have a slight difference, which is mod-affine. And these are exactly the schemes that satisfy the pairs that satisfy these two theorems in arbitrary dimension. So that's what I want to talk about.
There's a tension between choice of an embedding of the final field, an embedding in C and the conjugation with I. So you'll explain it.
Oh, what? Everything is over Z, so there is no choice. So my point is that if you, but of course, if you want to work over a general number field, then you just, I mean, any scheme over OK is a scheme over Z. So you just, it's easier to state the theorems of the Z, and then you do the Galois, and then one needs to do the Galois exercise to say. So of course, yeah, maybe, so thanks Dan. I should stress that this encompasses also results over any number field just by considering any number field as something over Q. Okay, and then you get, you know, the kind of things that you'll get is that if you work, over a general number field, you'll get different embeddings, and you need a bunch of compacts at all places, and then they need to be Galois conjugate in the usual sense. But I think it's easier to state everything over Z, but it encompasses everything. Okay, so before actually stating some actual theorems, I want to give you the geometric analog of this. So why are these statements, Fekete and the approximation statement, related to affineness, to some notion of affineness? And so I want to give you a very easy, a much easier geometric analog of Fekete, which is due to Hartshorne, essentially, and Goodman. So, geometric analog. Okay, so now I will work over a field, so K is a field. And then, okay, so first, the definition that I want. So we take X over Y, a morphism like this. So a morphism between, let's say, separated K schemes of finite type. Okay, so this is a modification between such schemes. So this is some kind of a birational morphism. So I want two things. I want F to be proper, and there exists F inside Y, some finite subscheme, such that F is an isomorphism outside above Y minus F. Okay, so this is so F. What F does? It's a morphism. It's birational unless Y is finite, and then it contracts a bunch of complete subvarieties of X on 2 points. Okay, so essentially F is some kind of blow up of points on Y. So that's a modification. Okay. And so the theorem that I want to talk about is the following. It's the theorem of Goodman and Hartshorne in 1969. And I promise I will come back to Fekete. No, a proper scheme is fine. So you can definitely have, I mean, a proper scheme mapping to a point is completely fine. Okay, so X scheme separated of finite type over K, and then the following are equivalent. So this is a very nice theorem. So first, there exists Y and a modification f from x to y, and unification with y affine. Okay, so first, the first condition is you can get x by blowing up points in an affine variety. Okay, okay. And the second thing is analogous to Serre's criterion for affineness. It is the following thing. So if you take any coherent sheaf on X, you look at hi xf. This is a affine dimensional K vector space for all I positive. Okay, so let's just do a bunch of remarks. Of course, you all know Serre's theorem, which is X is affine if and only if for all f and for all I positive, hi xf 0. So of course, there is no coherent cohomology on affine schemes, and this actually characterizes affine schemes. And also what you know is that, well, if X is a proper scheme, then definitely all cohomology groups of any coherent sheaves are finite dimensional. And if you put the two together, certainly if you get a proper map like this, a proper modification to an affine scheme, a very easy Leray spectral sequence argument tells you that all these need to be finite. Okay? And what Goodman and Hartshorne prove is that the converse holds. Okay? So let me just put a definition right now. So say X is mod-affine. So this is a modification of an affine if 1 and 2 hold. Okay, they are equivalent. Okay? So mod-affine schemes, there are some version of some interpolation between proper schemes on the one hand, if you take y to be a point, and affine schemes, if you take f to be the identity map. And somehow you interpolate between the two in a way that keeps this. So just to be careful, not any interpolation between proper and affine gives you, a mod-affine thing. For instance, P1 cross A1 is not mod-affine. It's not a blow-up of an affine variety, right? Because you cannot contract, if you want to contract the P1, you'll get the A1, but the P1 don't contract to a point. Okay. Okay. So maybe I should give you one example of how you get, there are many ways to get mod-affine schemes, but let me just stress two for some importance. So here's an example, which is due to Grauert of mod-affine schemes popping up. So let X over K be proper, and L a line bundle. Oh, this is due to Grauert and Grothendieck, I guess, depending on the exact setting. Then you can look at the X of L. So this is the total space of the dual. So this is a spec of the symmetric algebra, well, of L on OX, script L. This is mod-affine if and only if L is ample. Okay, so that's one criterion for ampleness. So let me just say how it works. Of course, this can never be affine because the zero section of L embeds in the total space, and it's a proper thing. And what Grauert's criterion tells you is that you can contract the zero section and get an affine scheme if and only if L is ample. So yeah, that's one thing. Okay, so this is one example. Another example, which is more related to Fekete's theorem, this is due to Hartshorne. let's take x, I think maybe, okay. I think x proper over k again, and d a divisor, a Cartier divisor. Effective in x with ample normal bundle. Then you look at the complement, x minus d. This is not affine in general because you can have you can blow up something in a projective variety. But x minus d is always mod-affine. You can actually blow down subvarieties of x minus d to points, proper subvarieties to points, and then you'll get into a situation where d is actually ample. That's here. Okay, so that's one example. And what I want to say is that in this setting, there is a version of Fekete's theorem that is fairly obvious once we have everything. Okay, so proposition, let x over k be mod-affine. Then there exists a maximal reduced proper subscheme of, let's say, z of x. So I look at all proper subschemes, there's actually a maximal one. So there are no infinitely many components or anything like that. And this is completely obvious, right? X, you can map it by a modification to something affine. So in the affine thing, there is nothing. There is no complete, proper, I'm sorry, purely positive dimensional. Of course, there are points and there is no maximal thing. But if you just look at any positive, so the proof is this. Consider f from x to y. Then, so a modification with y affine. Then if I look at any positive dimensional proper thing in x, it has to map to a bunch of points in y. So it means that it's contained in the exceptional locus of f. And so conversely, because f is proper, the exceptional locus is proper. So z is the exceptional locus. Okay, so there is nothing. But if I try to get a little bit more close to what we were doing, so in arithmetic geometry, of course, the whole point of the problem and the interest of arithmetic geometry is that we always work over z, which is a curve, and we don't have a base field. So let's see what happens when we have a curve. So assume that I have x to c. So this is a curve. And OK, so it's very easy to see. So I didn't tell you, but in the same way that there is a relative version of affineness, we can talk about affine morphism, we can talk about mod-affine morphisms. I won't write the definition down. But of course, if I have x which is mod-affine and it maps to a curve, then this has to be a mod-affine morphism. So let's assume even that this is affine. Okay, so let's take an affine scheme over a curve, and this is, this maps to k, to spec k. And let's assume that this morphism is affine. Then I look at the exceptional locus, it's just going to be exactly the multi-sections, so a proper curve, I'm sorry. This is just going to be the multi-sections of pi. So z is the set of multi-sections of pi, because of course any positive dimensional subscheme of x, it cannot be contained in the fibers because the morphism here is affine, and so I just have this.
Wait, are you assuming that x is mod-affine?
Yes. This is an example of a special case of the proposition. So x is mod-affine. Let's assume it maps to a proper curve by an affine morphism. Then the theorem just tells you that you have finitely many multi-sections. And this is exactly the way I want to understand Fekete's theorem. You have finitely many arithmetic curves in my scheme xk. Okay? And so that's why I want to. So that's my analog that I want to work out. I want to make sense of it in arithmetic geometry. And I should stress that I will get into arithmetic geometry, so C will be something like spec Z. And of course, there is no argument where I can contract arithmetic curves in arithmetic geometry because I don't know what it would contract to. Okay, so I want to give one last statement in the geometric case that I will generalize in a little bit, and then I'll pass to the arithmetic case. So this is also a very easy thing, which is a little less trivial in the arithmetic setting. If I have a mod-affine scheme, I can understand exactly how to compute the cohomology. So the cohomology is now finite dimensional, and I know exactly where it comes from. It comes from the exceptional locus. So may you understand the cohomology of sheaves on the mod-affine schemes as follows. So, okay, X mod-affine. Okay, so let's take X to be mod-affine and F coherent. Let's assume I just want to understand H1. So I just want to give you one statement. Then I have Z, the exceptional locus. So this is a subset determined by the proposition.
When you say exceptional locus, you mean only the positive dimension?
Yes, this is exactly the Z of the proposition, the purely positive dimensional.
So that's the definition?
Yes. So, but you can take, so this is this one, but you can take, there's always a canonical modification, because if you take any modification, you take the Stein factorization, so there is one with connected fibers, and then this is also the exceptional locus of this one.
So you don't have, if you have an embedded point in X or something, then that,
yeah.
That's not.
No, that's not. This is a reduced, purely positive dimensional one. Okay, so you have this one, and then where does the cohomology of F lie? Well, there is no cohomology when I push forward F to Y, of course, because Y is affine. So I just want to say, I can look at H1XF. This injects into a much larger space, but let's still leave it at this. I can complete X over Z and have. Okay, so actually all the cohomology is concentrated on the completion here. So this is very easy by the lower spectral sequence, and I guess the theorem on formal fibers. Okay, so I want to say, in this setting, this is very easy, but the cohomology is concentrated around that. Again, this is in a setting where we cannot contract Z. This is going to be a little bit less clear. Even more distance. Okay, and so this is a cohomological statement that I will come back to in the arithmetic setting. So now, my point is that what I want to do next is to give you a definition of mod-affine schemes in arithmetic geometry that is valid in arbitrary dimension, and tell you that these satisfy Fekete's theorem. And then I will tell you that the arithmetic surfaces for which this condition holds are exactly the ones where Fekete's theorem applies. Okay, so for this, I need to talk to you about A schemes that I defined a little bit earlier, and their cohomology. So of course, I want to stress, I just said it, but if I want to define affine schemes in this context, or mod-affine schemes, well, first, I don't have a very good definition of affineness, and I cannot use definition like I'm going to contract to a specific subvariety or this kind of stuff because of integral points. So there is no, as far as I know, I don't know how to define an affine scheme by a geometric condition in the setting I'm going to talk about. But what I will tell you is that I have cohomological invariants that allow me to give a definition in the sense of Serre or in the sense of the theorem of Goodman-Hartshorne. So the affine and mod-affine schemes are the ones with no cohomology or very little cohomology, and then I will work with that. Okay? And of course, the way I test that on a compact in C will be by computing the capacity. Okay, so let me put the definition of A schemes again. So an A scheme is a pair, okay, So curly x, which is xk, with x over z separated, finite type, and k inside x of c, compact, and conjugation invariant. Okay, so again, of course, this encompasses also schemes over arbitrary ring of integers of number fields, but it's easier to just work over z. And then a coherent sheaf on x is just a coherent sheaf on x, on the script x. Okay, so when I say coherent sheaf on curly x, this is just a coherent sheaf on the scheme. There is no metric data, there is nothing. Okay, so here is a bunch of examples that are very important. So first, any scheme over FQ is an A scheme. If I have a scheme over a finite field, then of course there is only one way to choose a compact, which is the empty set. So schemes over finite fields count as A schemes with no choices. So there is also one case where it's easy to choose the compact, where there is a natural choice of the compact. If X is proper, over Z is proper, we have X bar, which is a compactification of X, which is just X, and then I take the whole thing, X of C, as a compact. But I want to stress, K is part of the choice of the data. So everything depends on K. So these are two examples, but I have more complicated stuff. So of course, you can play with like total spaces of Hermitian line bundles, Hermitian vector bundles, and get interesting examples. But anyway.
What does the letter A stand for?
Arithmetic or Arakelov, depending on your taste. But Manin also uses a little bit of A objects in some texts where he investigates Arakelov geometry, so that's why we put something like that. So the point is that we really want to call them arithmetic schemes, but this is already taken, so this is a way to say that without sort of running into problems. So this is an A scheme, and so maybe the motivation is the following. So we want, so this is a very, very classical topic. We want to work in arithmetic geometry, so we work over spec Z, but of course spec Z is not compact, so you sort of compactify it in a way by adding some Archimedean data, right? And so the K sort of is a shadow of the model of X at the fiber at infinity. That's what we want to look at. So the analogy is the following. If you take a scheme over QP, let's say, okay, let's start with X over QP. So given a model X over ZP, so we get a compact subset, which is just the integral points, the ZP points of curly X, they map, okay, so maybe this is separated, I guess, inside the QP points of script X, and this is compact, because ZP is compact, and okay, maybe everything is of finite type. I didn't put any assumptions. And so in a way, I want to think of K as the integral, like the points that extend at infinity. This is a way of having this kind of, this is the Archimedean analog of this situation. Okay, so anyway, this is just a definition, so this is not that interesting. Of course, I don't have time to write all the details, but there is a category of A schemes. So you can say when an A scheme maps to another, it's a map of schemes that sends one compact to the other, and so on. And OK, so why can we work with them? So my goal, as I said, is to define what it means for an A scheme to be affine, and I want some cohomology. And so the point of the definition of A schemes is that we can do cohomology of coherent sheaves to an extent with them. Okay? So let F be a coherent sheaf on X, which is just a pair, xk. And OK, So let's think, I want to understand the cohomology of F. So the fantasy that we have, of course, is that xk is actually not just a relative scheme over spec z, it's some kind of scheme over a field, like maybe F1, we don't know what this is, but we want to study the cohomology of coherent sheaves, not the relative one to spec z that we can do higher direct images and understand, but we want to do some kind of global thing, right? And if you think about it, then the way you're going to compute it is just push everything forward to spec z, okay, so that we know how to do, and then we just need to understand h0 and h1 on spec z, on some spec z bar maybe. Okay, because spec z is a curve, so there's not going to be much more. And so I want to tell you how to do this. So I'm not going to do all of this, but I'm going to do a little bit. I'm going to study the first direct image of f, so this is just h0 curly x f. So this doesn't make sense because curly f is a complicated object, but I will tell you what kind of object this is. Okay, so first we have h0 xf. So this I cannot say that much about it. So f is a coherent sheaf, x is a scheme over z, finite type. So this is an abelian group, and this is countable. Okay, so maybe it satisfies a little bit more, but let's just go with the countable abelian group. So it doesn't have, I mean, x is not proper, so this might be, infinite ranks, there might be some divisible elements and so on. Okay, but I also have the data of the compact. So the way it goes is this certainly maps to h0 of k and f analytic. Okay, so this is a restriction map. If I have an algebraic section of f of the integers, I can restrict it to this, and this is just, by definition, the section of a sheaf on a closed set. This is just the limit over all u containing k of h0 u f analytic. This is the analytic section defined on the neighborhood of k. Okay, and suddenly I have a restriction map like this. But this is a sort of a different kind of object. This is a complex vector space. But this has a topology. Okay, because by general analytic geometry, if I take a coherent sheaf on a complex analytic space, then this is a Fekete space. This is a complete topological vector space, which is Fekete. And this is the limit of all this, so it inherits some kind of direct limit topology. Okay? So you look at this a little bit, and actually, the way you may define the topology is by a decreasing sequence of norms. So if you think about it, Fekete are defined by increasing sequences of norms. But let's see, here's the topology on h0 kf analytic is defined by a decreasing sequence of Hermitian norms. And so on. Okay? And the way, so what are these norms? So in the good cases, these are the L2 norms. You can take L2 norms on neighborhoods of K. Okay? These are the Hermitian norms. So, okay, so we don't care so much about this. I mean, we don't care. Of course we do, but the total package is that we have this kind of decreasing sequence of norms, and actually we have even something better. So we may arrange that they decrease very fast. So the relative trace, if I have two norms on a vector space, I can look at the relative trace, and this is always finite. So this is a very fast, quickly decreasing sequence of norms, and this is so-called a nuclear space in functional analysis. So you take an orthonormal basis for this one, and you sum the squares over the small one. Okay. This is a trace of the base change matrix between the two forms. Okay, so we may arrange this. This is a very classical condition in functional analysis. We get a nuclear space. Okay, and these may be just a bunch of notations. These are called the controlling norms. So norms that. Okay, so this is a whole package. So H0XF is exactly this package of an abelian group mapping to a nuclear space like this. So a space whose topology is defined by a decreasing sequence of norms that are nuclear with respect to one another. So this is a whole package, okay? So I call it like this. So A and Z is a category of pairs, M and a bunch of norms as above. So this is an abelian group, this is the norms up to equivalence. What interests me is the limit topology. So this is arithmetic nuclear spaces. And the way I want to think of it is as quasi-coherent sheaves on spec Z bar. So more or less, I don't want to say that this is a definitive thing, but this is something like quasi-coherent sheaves on spec Z bar. So I put the bar because spec Z is proper over spec Z, and this is a scheme with spec Z and just a compact at infinity, which is just a point. Okay? Okay, so this is what we want. So of course, this is a very complicated package because you have this topological condition and you have this abelian group, which might also be very big. But the point is, and I'm not going to explain more about it, but we can actually work with this. We can actually work with it. See that thing?
Is each norm defined on the entire space?
No, it's a limit. Right, because any element on HK is defined on some open, and then you take.
Okay, so just eventually.
Yeah. So the kind of space that you get is direct limit of Hilbert spaces. You take the union of Hilbert spaces with decreasing norms, like this, and you take the direct limit of this. Okay, so we can do cohomology a little bit. Okay, so first, given a pair, M with a single norm. So this is an abelian group. This is a Hermitian norm. Maybe my abelian group should be countable, otherwise everything becomes trivial. But I certainly don't want to be fine and frank. And I can do a little bit of geometry of numbers with this, and I can have cohomological invariance. Okay? So define H0 of this. So this is something like some kind of version of quasi-coherent sheaves. So I'm going to put a theta because there is a theta function there of M. So this is M bar. I'm just going to define it as a log of this. Okay, so I have an abelian group with a norm. I just take the theta function of the lattice, which is not a lattice here because the rank is infinite, of this. So this sort of counts how many small points in the lattice there are. I take a log. This behaves like a dimension. Okay, so I get H0 theta of this. This is some kind of H0. So I put small H0, some kind of small H0 for vector bundles on curves. And H1 theta, okay, so there is a lot of work to be done here, but H1 theta of M bar, so if you think of Serre dualities, it should be H0 of the dual, so I'm going to put it like this. But if you pay attention, this is very bad because the dual of M is not countable anymore. So you have to work. But OK, so we have H1 theta for this. And now, OK, so this is very much related to some kind of geometry of numbers invariant of M, like how many small elements there are in M, a lot of things like this. So there is a whole theory of doing geometry of numbers with these invariants. That's not what I want to stress today because I don't have so much time. But yeah.
It's just an notation.
Yeah, this is because there is a theta function and because it just put H0, it seems right. And so, yeah. And so the way you should think about it is that this is the dimension of h0 and h1 over the base field with one element, whatever. And these are real, so these are some dimensions, but they are, because we are in sort of a non-standard setting, these are real numbers. And one very important thing is that, so as I will explain, this will allow us to do cohomological proofs using these dimensions. But I don't have any vector space underlying that, I don't know what it is. And also the dimensions are real numbers. And it means that there is a very big difference between the standard cohomological proofs, is that a lot of cohomological proofs, you say, okay, so the dimensions of my sequence of vector spaces decreases, so it has to be constant eventually, and then some maps are surjective. And here, of course, you have decreasing sequence of real numbers that definitely exist and are not constant. But, you know, that's life. So you have this.
Can you repeat what this in quotation mark h0 is?
So I'm saying that this is not a good definition because this is not, the dual is not countable. So if you just do a naive thing, then it will give you nothing interesting. But I'm saying that in a way, so this is a countable abelian group. This is a direct limit of finite dimensional things. So this is an inverse limit. And so you sort of work with that. So you have, there is a lot of work to set up a good theory of the dual and how it works. But for all intents and purposes today, I will use this. Okay, so these invariants are interesting. So maybe, so these invariants are cohomological. So they are subadditive, which is not completely obvious in exact sequences. So one thing that is really important with h0 is that if you have a short exact sequence of objects with metrics and so on, so I don't want to do the whole setup here, if you had cohomology, you would have a long exact sequences, and it means that the dimensions of everything would be controlled by one another, right? For instance, you know, h1 of the left thing control h0 of the other ones and this kind of stuff. So any inequalities that you can write for h0 and h1 for usual vector bundles on curves, you can write it with these small h0 and h1. So you have to prove it, but it's a fact of using some kind of Fourier analysis, this kind of thing. So you can. So my point is that you can compute these invariants. You filter, you compute for small pieces, and then you add everything up. Maybe you try to understand how some series converge and so on, and then you get this. So what it means is that we can say whether an object of A and Z, now I come back to my category here, the kind of object that I get with coherent sheaves on A schemes. Okay, so now I don't get a specific norm, I just get a bunch of decreasing norms. So I cannot speak of the value of the theta invariant because I don't have one norm, but I can ask whether these invariants are finite eventually. Okay? To have finite. Okay, so I'm just going interested in cohomology, so let's say h1 theta. So this means that finite for some of the norms. Okay? So this is, I can say at least whether the cohomology is finite for this. And so now I can come to my definition. You can say that whether it's finite or even zero, actually. The actual number you cannot say, but anyway. So this brings me to my last part, which is mod-affine these schemes. Okay, so first the definition, let's work out the relative setting. So first, I want to understand what it means for an A scheme to be mod-affine over spec Z. So say X, okay, is relatively mod-affine. So I'm just putting the two definitions at once. So either affine or mod-affine. If, okay, so I want a relative notion. So first, I want the scheme X to be mod-affine over spec Z. And I need to work out exactly what it means for this to be mod-affine at infinity, some kind of relative condition at infinity. So there are many ways to work it out. So there are many ways to work it out. So you can definitely give cohomological versions, but I'm just going to give you the right answer that you can motivate. So X is already affine, but you want the pair. So the condition is that K is holomorphically convex. So this is the analog. I'm not going to write it down, but I want K to be holomorphically convex in X analytics. So this is a Stein variety. And essentially, this is the analog for homomorphic function on convexity, which is a condition on linear functions, okay, on K. And I need it to contain all positive dimensional proper subvarieties. So you have many, this is a very natural condition. Maybe I could say this is equivalent to having a PSH function on, so this is equivalent to having a PSH function on X, which is exhaustive, where K is the locus where this function is smaller than 1. Okay, so this is a natural condition from the point of view of complex analysis, and this is also a cohomological condition on direct images, but I didn't talk too much about this. Okay? And in dimension 1, I should say, if you think of Fekete's theorem, in C, K being holomorphically convex, it just means that the complement is connected. It's a very basic condition in dimension 1, then it becomes interesting in higher dimensions. Okay, but that's not enough, right? So in dimension 1, it can take X to be A1, and then K to be anything with connected, which is not an analysis, which is connected complement. And okay, but that doesn't give us any capacity condition. And now I want the final condition, which is actually mod-affine in an absolute sense for the whole scheme, not above spec Z. So X is mod-affine, so not relatively, if so I say, because this works for, if you remove the parentheses, it works for the definition of relatively affine. So it's a resp, but if X is relatively mod-affine, and okay, so once you have this, so you can say for all F coherent, I look at H0, XF, and I want this to have finite, respectively 0, H1 theta. I want H1 of this to vanish. So if you think in terms of low-res spectral sequence, again, which doesn't work completely here, but this is the only place where cohomology can show up, this H1 of the first direct images, because there are no higher direct images, so this is the only thing that can come up. Okay, so this is the definition of mod-affine. Example, for K inside C, let's say K equals K bar, and let's say connected complement. So this did not show up in Fekete's theorem, but in a way you can make it show up. It doesn't change the capacity. Then K, so A1 Z K is mod-affine if and only if the capacity is smaller than 1. And the way you want to think about it is, in a way, xk, this is a complement of the point at infinity in P1 with some kind of open subset, which is a complement of k. You can define a normal bundle to the point in that setting, which is a Hermitian vector bundle. This is exactly the ampleness condition. So this is a condition that tells you that A1k is a complement of a divisor with ample normal bundle in an arithmetic surface. So this is a natural condition. And so I want just to state the two theorems. I don't want to talk about, I won't talk about the proofs.
But the capacity of an analysis is not finite?
What? No, but in relatively, the relatively, what? I'm sorry.
Didn't you exclude
Yeah, so I want to do Fekete's theorem. I don't allow for annulus. I'm saying the condition is for this. But if you take the annulus, you take the interior, then it's not going to change the capacity, I think.
I mean,
yeah, so my point is that the natural thing is first, if you want to compute everything, just fill out all the holes and then state for this. But in higher dimension, because the holomorphic convexity condition is more complex, then you cannot, I mean, you could take the holomorphic, the envelope if you want, and then state it for that. Okay, so now here are theorem 1, the analog of Fekete's theorem, let X be mod-affine. Then there exists a maximal positive dimensional, let's say reduced, otherwise I can take thickenings, subscheme proper. A subscheme, so I call it Z. So proper means exactly this. It means that Z is proper and the compact is everything in X. A purely positive dimensional, all components. Okay, so what is an A subscheme if you think about it? So it means that Z has to map to X, so Z is a subscheme of X, and Z of C is inside the compact. Okay? And so if, okay, so let's call it X, script X and K. So if X is affine over Z, then Z is just a bunch of curves, just arithmetic curves. Namely, integral points that completely lie in the compact. This is exactly the condition. Okay, so this maximal subscheme is this. So this analog of Fekete's theorem, you recover exactly as I sort of hinted at, both Fekete's theorem and even Rumeli's version, but you get it in higher dimension. This kind of finiteness. And here is theorem 2. But the whole point is that you have to sort of bypass the geometry of it, because a mod-affine scheme, you cannot contract it to an affine scheme, because you cannot contract, you can contract everything to get something relatively affine, but that you get a bunch of arithmetic curves that you cannot contract. So in a way, you sort of hit a wall there. And theorem 2 is exactly this, so X mod-affine, let's say Z as above. Okay, so this is the maximal thing. And let F be a coherent sheaf. And let's take S, now a section of F on K. Like this, so this is a section of the analytification on a neighborhood of K. Then S can be approximated on a neighborhood of K by elements of H0 x F. Okay, so these are the integral algebraic sections of F, if and only if S bar equals S, so S is conjugation invariant, and then S comes from an element of H0, I can complete X, Z, F. So this means I look at the restriction S to the completion, I want this to have integral power series. I want it to be integral on the maximal subscheme. So this is exactly the condition. So if you think about it, if X is C, K is a compact, F is just the sheaf of regular functions, this is just polynomials with integer coefficients, this is holomorphic function on the neighborhood of K, and this is a condition of having a power series that is integral. Okay? And so, okay, so the proofs, I don't have so much time to say, but the point is that there is, as I said, this kind of theta-1 invariants are cohomological, so you can sort of, they work well in as soon as you put some finiteness here, they have very good functorial behavior, they have a good behavior with respect to exact sequences, and they do two things. First, so they behave well enough that you can prove, that you can state and prove that the cohomology of coherent sheaves on X is concentrated around Z, around the completion of X around Z. So you can prove a statement like this, so you have to state it, that the cohomology lies all there. And then there is a whole thing that we developed, that these invariants in the nuclear setting are related to geometry of numbers. Namely, the theorem that is behind is that if you have some kind of arithmetic nuclear space, so this space with many norms that decrease very fast, you have finiteness of this h1 theta. This exactly means that the covering radius of the lattice, of this infinite rank abelian group, is actually vanishing at its infinity. So if you mod out by something finite rank, then the covering radius is 0. So this is, in a way, so I don't want to talk about this, I don't have time to talk about this, but these h1 theta, they both have a cohomological behavior, and they control sections in an Arachelevian sense. They control geometry of numbers in infinite rank, and that's the start of doing this kind of algebraic geometry in this setting. So thank you very much.
First questions.
Yeah, that's I don't know. That's a natural question, and I think it would be worthwhile to sort of exactly think where. So I think there are affine and mod-affine varieties lying around in lots of places of arithmetic geometry, and so we have to think a little bit about it.
So I haven't seen this notion of capacity before, and so I'm just having a little trouble getting an intuition for it. So maybe you say like what goes wrong with like Fekete theorem, things like that, if you have something with capacity greater than or equal to 1. Like,
well, if you take a disk, okay, just take a disk of radius strictly bigger than 1. Then you have infinitely many algebraic integers lying completely in the disk. No, roots of unity. Just roots of unity and even.
like the unit circle.
Yeah, exactly. So for us, the capacity for the unit disk is the radius. For a disk around 0 is the radius. So if it's smaller than 1, then if you take any element that is completely in the disk, then the norm of it needs to be 0, so it's 0. If you take bigger than 1, then you get all the roots of unity inside. And so this is the right, so it measures the size in the sense of complex geometry. If you have a complex manifold, then you can hook up sizes in that way. So yeah. So it's really, capacity is really related to electrostatics. So it's the capacity of, all these points that I put, I put the maximal product of distance of the points. It's like, you imagine you put points with an electric charge and you put them and then they will repulse each other maximally, and these are the ones. And so the larger, if you have a larger compact, then it's sort of, they have more space to lie around.
If there are no more questions, we're going to have a coffee break now, and we'll meet again at 11, and let's have